Welcome back. Today's topic is supercells. I wanted to pick a day out of this campaign to focus specifically on supercells, the nature of these storms, and the destruction that they can do. I like to refer to these as the king of all thunderstorms because they're quite simply the most powerful of all thunderstorms. They are the most severe of all thunderstorms. And a lot of people are not aware of supercells and what they are. So I think it's really important that we emphasize these storms because we definitely get them here in Indiana. We don't get them all the time, but we definitely do get them. And so I think it's important to bring attention to these storms. It's important for you to understand their power and what they can do. These are the storms that produce the strongest of the tornadoes, typically the most damaging hail. And we'll start here with the definition of a supercell. Supercell would be any thunderstorm with a sustained rotating updraft, which is what we call a mesocyclone. You remember in the last video about tornadoes, we talked about how the shear within the atmosphere sustains that rotation into the updraft of a thunderstorm. Well, this is a diagram of this is a picture of what a typical thunderstorm looks like. We've talked before about instability and how the instability adds fuel to basically help construct the thunderstorms, if you will. So the instability, we got it from the sunlight here. It's rising, it's condensed with the moisture, it's led to this towering updraft. And now we have a thunderstorm. This right here, basically the center portion is what we call the updraft. So now we've got moisture in here, we've got raindrops. The inflow is being pulled upward into the updraft, so the raindrops are being pulled, they circulate, they fall back out, and eventually the updraft can occasionally reach to a point up in the atmosphere where it hits basically the freezing mark, because the upper layers of the atmosphere can be a lot colder than the lower layers. And when the raindrops hit that freezing area, they freeze into hailstones. So basically, they continue to climb, get pulled upward until the updraft is no longer able to sustain them, basically. They circulate back and they fall down. That's how you have your rain, and that's how you get hail. The larger the updraft, typically the larger the hail will be. And here's another more complex picture of a storm. Now this is a supercell. What we were showing you on the last slide was just a typical thunderstorm, but this is a typical supercell storm. And again, we do note similarities. We do have the inflow again being pulled in, the instability allowing to the construction of this nice updraft. But we notice something a little different here. We see this little spiral circulation here within the storm. This is the rotation that has been produced by the shear within the atmosphere, and this is our mesocyclone. You can see right here that it kind of allows the thunderstorm to take on a little more of a tilted, kind of a more tilted updraft. You can kind of see the little tilt here, and that's one of the ways you can kind of look. If you're looking at, because thunderstorms can look alike, especially in the summertime when you're looking at them from a distance, if you're standing outside and you see an updraft. But these supercells tend to have these tilted updrafts from the mesocyclone. And so that's one thing to keep in mind. And again, you have the rain falling, you have the hail falling. Over here you'd have your shelf cloud, you have the cold outflow here from the rain, the hail. And then right here, ta-da, you have your wall cloud and your tornado right under the mesocyclone. And so in this case, if the storm, say it's moving in this direction, as you can see, the people right here, anybody who happens to live here, they're going to get rain first, then hail, and the tornado. That's why you'll hear people often say that the hail precedes the tornado, because that's what happened. That's what would happen in this situation. And the thunderstorms tend to move in such a direction where the rain and the hail will almost always precede the tornado. So these people are going to get pounded by heavy rain, large hail, and because of the intense precipitation out ahead of the tornado's not going to be very easy to spot. It's going to be very difficult to spot, probably almost impossible to spot. And that is always something to keep in mind when you have one of these things heading in your direction. The heavy rain and the hail will often obscure the tornado. We have a few different types of supercells. HP, which would be high precipitation. Those tend to occur, we see a lot of those at least east of the Mississippi River, where we're right above the Gulf of Mexico. We have a lot of moisture, basically just surges northward, so a lot of moisture. We can also see these type of supercells when we're dealing with a warm front situation. Then there's LP, which is the opposite, a low precipitation supercell. These tend to occur up in the northern high plains, just east of the Rocky Mountains, where moisture has a difficult time reaching those locations. You can still get storms, and you can still get these supercells that can produce hail and tornadoes. It's just that there's typically a lack of precipitation. The hail might not be quite as large as what you would see in another supercell because of that real lack of moisture. But these can still produce a fairly significant hail, some tornadoes. If you look at them, you can also see the updrafts are a lot smaller, and so it can almost kind of appear as harmless, which can be a little misleading because they can still again produce tornadoes and hail. Then you have your classic supercells, and these are common when you have a DRYLINE situation. These are the types of supercells that grab a lot of attention from storm chasers. We have a lot of photos of these kind of supercells, and probably the most recognized type of supercell in the storm chaser community. We'll talk about that here a little more momentarily. And then there's another type here. I didn't really mention it because it's kind of more of a classification under the HP group. But we have, in addition to the HP high precipitation supercell, you can have an HP, what we call low topped supercell. And that is basically a situation that occurs when you have a lot of wind shear in place, but only marginal instability. Just a little bit of meager instability in place. We've talked about how you really need at least some instability, because without the dynamics, you're basically just going to end up without the instability. Even if you have a bunch of dynamics in place, a bunch of strong wind shear, basically just going to end up with a rainy day. However, if you have some instability, and even the most meager, even if it's just a little bit of marginal instability, you can as long as there is something there to make that updraft grow just a little bit, you can still get a storm. And if that updraft goes and it hits the wind shear, it can still sustain rotation, even if it's small. And that's what often happens when you have severe weather setups during the wintertime. The updrafts don't go very large, but they still tap into that stronger shear, and they can still become rotating thunderstorms with mesocyclones, and so they can be low-topped supercells, is what we call them. Low-top because the top of the updraft does not grow very large. And so those storms tend to be small. They don't look very bullish on radar, but they can still produce tornadoes. They're not much of a hail threat with those storms, but they can still produce tornadoes, and occasionally even rather strong tornadoes, and that is something to keep in mind, especially during the wintertime. This is just a picture of a supercell. You can kind of see what we're talking about. Updraft, and we got this top, basically a cloud deck here at the top. Is what we call the anvil of a supercell. This is this is a classic look at a HP type supercell. You can see a little appendage here, but a lot of moisture, a lot of heavy rain, some hail there. A typical HP structure. This is more of a classic looking supercell. This is from the more 1999 tornado, not the one we had recently in 2013. But yeah, that's about as close as we ever get. You got heavy rain, probably some hail here, and you also have a little bit of a debris ball signature. Wish I could go back to that, but we talked about the debris balls in that last video here, and I believe we'll have another example coming up where we can show that off a little more. So we talked about how classic supercells like dry lines, a boundary which is basically a boundary that separates the dry air from the moist air. This is a very common occurrence out in the Great Plains. You'll have a dry line in the area, and basically you'll have moisture go up ahead of the dry line, and you can have everything else in place, the cold front, you can have the strong dynamics, but even that dry line, which blows off of the Rocky Mountains, begins to progress eastward. And it's basically works as a boundary, which would be another triggering mechanism for storms to initiate. For example, I want you to look at this, and you can see the more colorful. You can see the more colorful. I can't talk again. You can see the red numbers, those are the temperatures. The green numbers are the dew points, which would be a measure of moisture within the atmosphere. And then these little gray things are what we call isobars to give us an idea of the wind direction. But you see this yellow thing showing up here, this yellow little boundary. This is the dry line. And I want you to notice something. Out ahead of the dry line, we have dew points in the upper 50s, low 60s. Typically, we want to see them a little higher for severe weather, but that can still be conducive to some degree. Real thing I want to point out is the dew points behind this dry line. 26, 37, 23. So there's quite a difference. Basically, this dry line comes off the Rocky Mountains, moves to the east, and it works as a triggering mechanism once it hits the instability, the moisture, and then when we have the capping inversion take place. That's cap is when you have warm air aloft that prevents other air parcels from the surface from rising. When that begins to erode, a lot of times these dry lines can create that inversion of the cap. So then you get thunderstorms going up along the dry line. And behind there, the dry line, though, even though you may have warm temperatures, the moisture is significantly limited because the dry line is basically pushing that moisture further eastward. And so since supercells like to go up along these dry lines because they act as a triggering mechanism, the tornadoes are often pretty visible. In an HP supercell situation, tornado might be visible to some degree, but oftentimes it gets wrapped up in rain. But when you have supercells go up along these dry lines, they are classic supercells typically, and since they are pretty much latched right onto the dry line, the tornado that develops is often visible because right behind that supercell there's a bunch of dry air, and so it does not get wrapped up into the heavy rain. And so, just a little summary here of supercells. They are the most powerful type of thunderstorm. They can last for hours. All hazards of severe weather are possible: large hail, damaging winds, tornadoes, and again, these are the storms that tend to produce the strongest of the tornadoes. Now, not every supercell produces a strong tornado. Not even every supercell produces a tornado. Probably most supercells do not produce a tornado. But it's these supercells, these really intense supercells, that are the storms that do tend to produce these stronger, more violent tornadoes when they occur. And so I think it's really important that we understand what a supercell is and kind of understands a little more how it works. And this is kind of a topic I'm wanting to focus on throughout the spring, so we might do even more videos here in the future to kind of focus on this these supercells, because I think it's important for us to understand them and how they work because of the danger that they represent. Again, most likely type of storm to produce a strong, violent tornado. And needless to say, they can be very dangerous. And so, when you're watching me talk about the weather on Facebook, and when I post about an upcoming severe weather potential, I want you to take any severe weather threat seriously, even if it's a squall line or if it's a more marginal day, because severe weather can kill in many different ways and shapes and forms. But when you hear me mention the possibility of supercells, that means you definitely need to be alert. You need to be prepared to take action, because these supercells tend to cause a lot of our problems. Thank you for watching, and I appreciate